Now that we've talked about molecular geometry, the spacing and orientation of atoms around the central atom of a molecule, we can actually incorporate that into something that we discussed early in Chapter 7, which was the idea of bond polarity. So remember, if you have two atoms with different electronegativities and they're bonded together, then the electrons spend more time around the more electronegative element and less time around the less electronegative element. And many covalent bonds are in fact polar to some extent. And now we can apply bond polarity to what we just talked about in terms of molecular shape to actually come up with whether an entire molecule is polar or not. It's not just as simple as whether the bonds in the molecule are polar, as we'll see. So if we look at an example like chloromethane, CH3Cl, the Lewis dot structure is shown here minus the electrons on the chlorine. The important part of this bond is the fact that carbon is much less electronegative than chlorine is. So you can see that chlorine has a partial negative charge there, and carbon a partial positive charge. So that bond is definitely a polar bond. You can see the bond dipole's been drawn in between the carbon and the chlorine in the second image. Now the carbon-hydrogen bonds are essentially nonpolar. Hydrogen is a little bit less electronegative than carbon, so I guess there are technically some small bond dipoles there, but really the only significant one is between carbon and chlorine. And if we look at the distribution of electrons in the molecule, shown in the heat map on the right, you can see chlorine has a much higher electron density than the carbon does. So that kind of makes sense if you think about it. And because of the way that the molecule is shaped, basically the bottom of the molecule in that orientation is electron poor, and the top is electron rich. So the entire molecule itself has a net dipole that points basically directly up in the same direction as the carbon-chlorine bond dipole itself. So chloromethane is a polar substance. It consists of molecules that are polar because they have polar bonds in an orientation that makes the molecule itself polar. Other examples of polar molecules, in fact some of the most important ones, especially the latter, are ammonia and water. So the bond dipoles are shown here. Both nitrogen and especially oxygen are considerably more electronegative than hydrogen is. So in both these examples, the bond dipoles are going to point away from hydrogen and towards either nitrogen in ammonia or oxygen in water. And in addition to that, the lone pairs themselves, there's one in ammonia and there's two in water, are electron rich. They're just made up of electrons. So when we take all those factors into account, we can see, for instance, in ammonia, the bond dipoles kind of in the horizontal direction cancel each other out, but all of the hydrogens are underneath that nitrogen, and so they're all pointing up. So there's still a net dipole from the nitrogen-hydrogen bonds that points up away from the hydrogens and towards the nitrogen. And that gets added to the fact that there's also another dipole pointing up due to the lone pair on the nitrogen. So the net effect is that there's a very strong dipole in ammonia that points away from the plane of the three hydrogens and up towards the top of the nitrogen atom. A similar thing happens in water, where the horizontal components of the hydrogen-oxygen bond dipoles kind of cancel each other, but the vertical components add together. And furthermore, the lone pairs on oxygen are also going to increase that effect. And so we get a net bond dipole that points basically from halfway in between the two hydrogens up towards the top of the oxygen atom. And so water is extremely polar as well. Now, it's not the case that just because you have polar bonds, like in the previous examples, that we're going to have a polar molecule. So pictured here are two examples where we have basically bond dipoles that cancel each other out. So with carbon dioxide, which is kind of the prototypical example of a molecule with very polar bonds that is still nonpolar overall, you can see that we have carbon-oxygen bonds, and in the electron heat map, you can see that the oxygens are more electron rich than the carbon, which at the middle of that molecule is very electron poor. However, since carbon dioxide is linear, and both of those bonds are identical to identical atoms, uh, both of those bond dipoles are individually pretty strong, but they point in the exact opposite direction as each other. So carbon dioxide has a completely nonpolar overall structure. In the case of carbon dioxide, everything is linear, so it's fairly easy to see. In the case of carbon tetrachloride, there on the right, it's a little bit less obvious because things are kind of in 3D and now there's 4 bond dipoles instead of just 2. But for a tetrahedral shape, which is also pretty symmetrical, each of those carbon-chlorine bonds is pretty significantly polar, pointing away from carbon and towards chlorine. But the overall effect is that all of those bond dipoles, when you kind of add the 4 together in 3D space, they exactly cancel each other out. They're all the same size, and they're in a symmetrical orientation where they cancel each other out. So for something like carbon tetrachloride, that's also a completely nonpolar molecule. So as you can see, there are plenty of examples where a molecule might be nonpolar even though it has some polar bonds in it. So what we're going to do next is a few examples that you can try on your own. So the first example asks you to classify whether phosphorus pentachloride is polar or nonpolar. You can see I've already drawn the molecule here on this slide, although when you do this you should try to get the correct Lewis dot structure on your own. And I'll let you try to think about whether this should be a polar or nonpolar molecule. Go ahead and pause the video, and I'll come back in a couple of seconds to go over this. Alright, so let's look at this example. Between phosphorus and chlorine, chlorine is significantly more electronegative than phosphorus is. In fact, phosphorus is less electronegative than carbon is, so it's going to have an even more polar bond between phosphorus and chlorine than you would between carbon and chlorine. That said, we have another situation where, if we kind of draw in all these dipoles, which are going to point away from phosphorus and towards chlorine, you might be able to see, hopefully, that these are going to cancel each other out due to the symmetrical shape of the molecule. In fact, it's a pretty safe bet that if you have a if you have an atom in the center of a molecule and it's surrounded by a bunch of charge clouds that are all atoms, so no lone pairs on the central atom, and combined with that, all of the atoms are the same. Whenever that's the case, you pretty much always have a nonpolar molecule, even if the individual bonds are polar. So despite the fact that phosphorus pentachloride has very polar bonds, it is itself a nonpolar molecule. So let's look at this next example, which will be not phosphorus pentachloride, but PCl3 phosphorus trichloride. So again, try to draw this Lewis structure on your own, see if you get the right answer, and we'll go over whether this is polar or nonpolar once you've paused the video, and we'll resume. So in the case of phosphorus trichloride, this is going to be a polar molecule. Now, again, each of these bond dipoles here are going to point towards chlorine and away from phosphorus. You need to be careful because we also have this lone pair of electrons here. However, the lone pair of electrons is going to have a different dipole contribution from the phosphorus-chlorine bonds. So these are not going to cancel each other out. So PCl3 is going to be a polar molecule. So you can see that we had two different combinations of the same two elements. One gave rise to a nonpolar molecule, one gave rise to a polar molecule. And for the most part, if you have a lone pair on your central atom, things are going to essentially be bent in a way that usually you'll have a polar molecule. Now, there are some exceptions to that, which we'll cover here in a second, but most of the time, whenever you have a lone pair on the central atom, you will have a polar molecule. So let's look at this example, xenon tetrafluoride. This is an example that we used for a square planar molecular geometry. So since we've already gone over this, I will kind of walk you through this example. You don't necessarily need to try this one on your own. So around this xenon atom, we have our 4 fluorines in a square shape, in a flat plane, and we also have our 2 lone pairs on xenon, and those are exactly opposite each other. So there's going to be one dipole here due to the lone pair, but that points in exactly the opposite direction of this other lone pair. So those two exactly cancel each other. And then if we look at the fluorines, the xenon-fluorine bond is going to be polar, points away from xenon towards fluorine. So these are polar bonds. However, they exactly cancel each other due to the symmetrical nature of the molecule. So this is going to be a nonpolar molecule. And one of the reasons I wanted to go over this one is the fact that xenon here has 2 lone pairs. So it's one of these examples where we do in fact have some nonpolar molecules that have lone pairs on the central atom. In fact, let me go back a few slides. I apologize for kind of the flurry of activity here. And I'll point out the handful of examples where you might have lone pairs on the central atom but still have a nonpolar molecule. So we just saw square planar. Those 2 lone pairs cancel each other out. So square planar molecules, if all the atoms on the outside are the same, will be nonpolar. And likewise, if we go up to our 5 charge cloud example here, a linear molecule, for reasons that are fairly obvious, is also going to be nonpolar if we have all the same atom attached to our central atom. Otherwise, if you have lone pairs on the central atom, it's probably going to be a polar molecule. And if you have no lone pairs, as long as all the atoms on the outside are the same, it's probably going to be a nonpolar molecule.